Okay, first of all, let me thank the organizers for giving me a chance to talk at this conference today. I will be talking about intersection theory, and the main object in my talk will be the moduli space of Riemann surfaces at a given genus G and with n punctures, so this is called MGN. And perhaps one of the most interesting applications of such a moduli space is the theory of two-dimensional topological gravity. And in this theory, you consider two-dimensional manifolds. You interpret them as Riemann surfaces, and then you can show, and that was conjectured by Witten and then later proven by Kontsevich, that all observables in such a theory take the following form. So you have some two forms or representatives of cohomology classes that you can wedge together, and you wedge them, you put enough of them so that you exhaust the dimension of the moduli space and simply integrate over it, or rather over its compactification. And then what you can show is that those things give you rational numbers, so they always integrate to rational numbers, and those rational numbers represent observables in quantum gravity in two dimensions, and they are called intersection numbers. So one of the questions that I was interested in is whether you can compute observables in some interacting theories in a similar way. Okay, so what about interacting theories? Of course, now observables can depend on some quantum numbers, polarization vectors, momentum vectors, and so on. So we need to endow the moduli space, we need to enhance its topological character with some additional structure. And I will argue that this additional structure is provided by the so-called local system. So if you're familiar with sheaf theory, local system is a locally constant sheaf. So this, I will explain this in a second. So this is turns out to be rich enough already at genus 0, and hence for the purposes of this talk, I will only discuss the case of MON, so the moduli space of Riemann spheres with n-puncture insertions. So it turns out that there are essentially two ways of constructing intersection numbers twisted by such local systems. And following the first path will land you eventually on a type of integrals appearing in closed string amplitudes. However, there exists a second approach, and that's something that was previously missed, and that will be the subject of today's talk. So within the next 30 minutes, we'll arrive at sort of twisted intersection numbers, which will turn out to take the following form. So it will become apparent that we can only have n-3 forms that belong to some cohomology classes that I will describe shortly. And hence, we can only put two of them together, integrate over the moduli space. And because of this twisting, what will happen is that the result will no longer be just a rational number, so not just a number, but rather a rational function of kinematic invariance. And I will conjecture that these compute tree-level scattering amplitudes in various quantum field theories with a finite spectrum of massive and massless states. So finite spectrum, here I meant to indicate that this is not a string theory, but rather a quantum field theory. And the physical interpretation of such formulas still remains an open problem. And in fact, that's a question that I can address to you. Can you construct some underlying worldsheet action which will reproduce the formulas that I will be talking about in this talk? So please keep this in mind. Excuse me? Yes, they will have associated momentum. So let me start off by reminding you about some. Perfect. So we can discuss it in the discussion section. So let me start off by introducing some basic aspects of MON. So MON is a configuration space of n points on a Riemann surface. So write it as CP1 modulo the redundancy group, which is in this case SL2C, which allows you to fix positions of free punctures. Therefore, the resulting manifold is n-3 dimensional and just parameterized by positions of the punctures minus the diagonals where I remove the collision points. Okay? So because of this removal of collision points, the resulting manifold is non-compact. Another topological aspect is that it turns out to be aspherical. So what it means is that the fundamental group, pi1, is the only non-trivial homotopy group, and it's generated by the following loops. When I have two punctures, Zi and Zj, when Zj goes around Zi, not encircling any other puncture, and goes back to itself, to its original position, I will denote this loop as this loop ij. And alternatively, you can think of the fundamental group as a braid group of n strands with 3 of them fixed. So this looks like, Zi goes in this direction, and you have Zj strand going around it. And finally, the last ingredient that will be needed for this talk is the fact that the Euler characteristic of the moduli space is this number n-3 factorial up to a sign. Very good. So now a local system described by this letter is just a representation of the fundamental group. So study of such local systems dates back to around 100 years ago by these authors. So representation means that I map the fundamental group to a space of matrices. And for the time being, in the first part of the talk, I will consider the abelian case, in which that will be just GL1C, so the space of non-zero complex numbers. And the map is given as follows. I take a given path in the fundamental group, and the only thing I can do is, well, I have a one-dimensional path. I can integrate some one form over it, and that gives me a number, and I just need to exponentiate it to first get rid of the 0, and second, to ensure the correct group properties. Very good. So now we need to choose some specific local system. And the specification of it boils down to specifying this one form that I put here, omega. Hence, I put it in the label for the local system. So this provides, we choose it to provide a map between the space of Riemann surfaces and the space of kinematic invariants. And it goes as follows. So omega here is given by a double sum over all punctures. For each of them, we associate some ingoing momentum called pi associated to a puncture zi. Then we put this dot product here and multiply it by a d log of the difference between positions of the punctures. So here you should think of zi's as inhomogeneous coordinates on each CB1. Very good. In the final step, since we need to exponentiate the result, it needs to be dimensionless. So we need to normalize it by some mass scale, 1 over lambda squared, and you can think of it as an alpha prime in string theory. Very good. So now, using this prescription of the local system, each loop is represented by this integral, and if you just plug in the values, it turns out to be this exponential of p dot p with some normalizations. Another interesting aspect is that since infinity is not a special point, so if I take some puncture zi and go around infinity, I can just contract it back to itself, so it should be represented by a unit number. But on the other hand, if you just look at this one form, it has tons of spurious poles at the infinity, and they boil down to this exponential if you evaluate this residue of zi going around infinity. So this gives us a constraint that on the on the p squared of each particle, that it has to satisfy, it needs to exponentiate it to 1. And therefore, we find that the masses are quantized in this half-integer multiples of the fundamental mass scale. Very good. So now we can consider the differential forms with coefficients in such local systems. So the way it looks like is that we have some k form on the moduli space, so here denoted by phi. And then we associate coefficients in this line bundle, which are just given by exponentials, starting from some arbitrary point that comes into the definition of this form, and integrated to zi's, where zi's are positions of the coordinates of this form. Very good. However, for the purposes of this talk, it is enough to consider an infinitesimal version of such forms, and they are governed by the following Gauss-Manin, or in physics known as KZ-like connections. Okay, so the way I construct the connection here is that I take the usual D, the RAM differential, and I twist it by plus or minus omega. So omega was a one form. This is this increases the degree of the form, so everything is good. And then I will choose a pair of those labeled by a sign, and I will explain in a second why we need to include two of those things. Yes. This part is single valued. This is multi-valued. It's still multi-valued. It's just not multi-valued around infinity, if I don't fix any puncture at infinity. So now, if you're familiar with the comparison theorem, then the top and bottom of the slides are connected by the comparison theorem. Very good. So now we have these connections defined on the previous slides, and since omega is a closed form, we have this integrability condition that omega squares to zero, and sorry, nabla squares to zero. And that allows you to define cohomology groups, which I will call twisted cohomology groups. So the way they look like is essentially is just a space of nabla closed forms modulo the space of nabla exact forms for both plus and minus. So it's just a twisting of the usual the RAM differential, the RAM cohomology group by this one form, which enters through the nabla. And the generic elements of the plus or minus cohomology I will just call phi plus and phi minus. So now we can use the result of Aomoto, who showed that only the n-3rd twisted cohomology is non-trivial. So what that means is that if you want to construct forms with such properties, you will find that only n-3 forms are allowed. Okay? So therefore, we will choose for the phi plus and phi minus from now on to be both holomorphic forms and holomorphic n-3 forms, sometimes also called twisted forms. So just elements of these cohomology groups. Very good. So now we have an additional condition coming from the SL2C redundancy on the spheres. And I'll just skip the math and tell you the result that it imposes the certain covariance properties under the action of SL2C, that phi plus and phi minus have to transform with this weight. And the only thing that I want you to take out of this is that the weight itself is mass dependent, just like in string theory. And that tells you that what forms you can call twisted forms is further constrained by the choice of masses that you put in. Remember that this here is an integer. Okay, so for example, if you choose all external masses to be just the same and equal to this capital lambda, which was some mass scale, then the examples of allowed forms for phi minus is just the integration measure looking like this, or you can put some SL2C invariant cross ratios here. And for phi plus, we need additional powers of z's in the denominators. So that's one example. When you build a chain out of this and you square it, it has the correct SL2C properties. Very good. So now we can give our proposal of how to construct intersection numbers of such cohomology classes. So the most naive way of doing this is that you take those two forms and then you wedge them together. Let's forget about the C for now. You wedge them together and integrate over the full moduli space. However, we made the choice that both phi minus and phi plus have to be holomorphic, and therefore you find that they wedge to 0, and that means that there's no contributions, at least from the bulk of the MON. However, since the moduli space itself is non-compact, close to the boundaries of the moduli space, there could be some divergences. Okay, so this integral could naively diverge, but on the other hand, this is 0. So we have a sort of a 0 over 0 problem that we need to regulate. And this 0 over 0 problem comes only from the neighborhood of the boundary divisor of the moduli space. That will necessarily also mean that if we manage to regularize it, the integral will localize on this boundary. So just to remind you, boundary of a moduli space are the degenerations in which punctures collide with each other. So they correspond to factorization channels in the kinematic space. Okay, so in order to make the above integral well-defined, what we do is we impose compact support on the integral, on the integrand, and the compact support has to be imposed on at least one of those forms. What it means is that we choose some phi plus c, c stands for compact support, which vanishes close to all boundary components, in such a way that at the same time it's cohomologous to the original form that we want to intersect. Okay, so you can do it by finding nabla exact terms such that this condition is satisfied, such that the left-hand side vanishes, and that's always possible to do. But it turns out that if you actually want to impose this compact support, it will give you some non-holomorphic contributions here in these exact terms, and that's exactly what will turn out give us this integral, first of all, to be convergent, because this phi vanishes close to the boundaries, so this is regulated. And second of all, it will have some non-holomorphic contributions, which wedge together with phi minus to give us a non-zero result. So let me skip this. So for example, performing explicit computations of such intersection numbers, doing the regularization that I just mentioned before, and taking the examples of phi minus and phi plus from a couple of slides ago, we'll find that what you find is that the result is given as a sum over all trivalent planar trees, and then you multiply together all propagators associated to internal edges of such trees. Of course, that's nothing else but just tree-level amplitudes in a trace phi cube theory with a mass. So more generally, what you can show is that such intersection numbers are always rational functions of kinematic invariants, and they also always have only simple poles of the following type, which is exactly what you expect from a local quantum field theory. So another example is that if you take these forms phi plus and phi minus, coming from superstring correlators, and what I mean by that is that you write some open string or 1/2 of the heterotic string in this form. You just strip away this global Kobayashi factor and call the result phi gauge. So phi gauge itself is a holomorphic n-3 form, and it's globally well-defined on the moduli space. So it provides a valid example of a twisted form. You can just plug it in here. Okay? If you plug it on one side, and then the other side you put with this sort of Kac-Moody thing, you find that the result becomes you can prove that the result becomes just the super Yang-Mills amplitude without any corrections, so just the field theory. And similarly, if you put two of these guys, you get supergravity. And these are exact results. So there's a period here and here. There's no stringy corrections. Very good. So some other examples, if you take logarithmic forms. So logarithmic form is the one with simple poles on all boundaries. they are associated with, they turn out to be associated to massless internal and external states, and you can prove that if you take both of those to be logarithmic, things localize not just on the boundary, but on the most degenerate places on the boundary divisor, which are the vertices. And each vertex corresponds to, is in one-to-one map with the trivalent trees. So they're the most degenerate places on the boundary of the moduli space. And all you have to do is just compute a residue around this vertex for phi minus, multiply it by the same residue around the same place for phi plus, and divide it by these denominators associated to these trivalent trees, and that's your answer. So let me address also a question: what happens in the massless limit on its own right, since that makes some connections to some results in the literature. So in the massless limit, phi plus and phi minus were defined by this. And remember that omega was going like 1 over lambda squared. So in the massless limit, this term just dominates, and this differential just becomes very simple. It's just wedging by one form. Therefore, the twisted homology groups degenerate. So now it's a space of holomorphic n-3 forms, quotiented by the space of omega wedge n-4 forms. And the quotient by the exact terms, for it to happen, it is enough to impose the constraints that omega is equal to 0. It just kills all of those things. And those constraints are known as the scattering equations, and they've been used in some formulations of scattering amplitudes by Kachazohe and Yuan a couple of years ago. So in fact, using Morse theory, you can show that intersection numbers localize on these constraints, or these scattering equations, and those constraints are known to have only to be just a set of n-3 factorial points in the bulk of the moduli space. And you obtain this result, and that result is the Kachazo et al. Formula. And it turns out that the right-hand side expression, so the massless limit, has an interpretation as a string theory in the ambitwister space. So that's a result of Mason and Skinner. However, by the Bell-Ruffini theorem, the algebraic solution of the scattering equations do not exist. So you can find them numerically, but not necessarily analytically, for n larger than 5. And what this means is that, well, to do explicit computations, we need some better setup. So here's in the final couple of slides, I will sketch a way of computing things analytically. And that's given by recursion relations on fiber bundles on the moduli space. So you start with the following fibration of the moduli space MON into n-3 one-dimensional spheres. So this is the sphere where Z4 lives, with Z1, 2, and 3 fixed. And for each point here, you find another sphere where Z5 lives, now with 4 fixed things, and so on, until you hit Zn. So for example, the Euler characteristic, let's do just a topological computation. You can find that the Euler characteristic of each sphere sigma p is that of a sphere, which is equal to 2, minus the number of removed points, which is p minus 1. So the result is 3 minus p. For example, here we find minus 1, minus 2, ... and here we get n minus 3. So the Euler characteristic of the total space is given by the product of those things, and it turns out to be this n minus 3 factorial. So what's the significance of this result? Well, another way of writing the Euler characteristic is as an alternating sum of the dimensions of cohomology groups. And I just said at the beginning that these are known all to vanish except for in the n-3rd case. And that means that the dimension of the space can be computed just as an Euler characteristic. And that result is due to Aomoto that the space of twisted forms is n-3 dimensional. And of course, it was later found also independently in the physics literature. So what's the significance of that? Well, we'll try to use this to do practical computations. So we use the fiber bundle structure to integrate out puncture by puncture. So starting from MON, I want to go to the moduli space with one fewer punctures, and so on, and so on, and so on, until we hit MO3, which is just a point, so there's nothing left to integrate. Okay, so it turns out if you do this is just a sketch, the rank of the local system now increases. So the representation is no longer a number, it's now a matrix. And that means that this omega generalization of omega now has to be, it's still of the same form when you sum up to p, since each of them is on MOP. But now you have to promote these things, this what used to be twice p dot p, into matrices. Okay, so those matrices are subject to some integrability conditions, which, however, doesn't fix them completely. So you need to make some choices, and it turns out that you can completely find them recursively, meaning that starting from the initial one, which was just a 1-by-1 matrix, you build these kind of matrices, and then you keep going until you hit the exhaust, the dimension n-3 factorial. So in the next step of the recursion, what we want to do is to do exactly the same, but for the forms. So our input of the computation were these forms or MON. And what you do is you want to integrate out the nth puncture to land you on forms on MON minus 1. And the result of that is that you decrease the degree of the form, but you increase the length of a vector in which this lives. So now this becomes a vector of dimension of length n-3. If you keep going, you find that you decrease the degree of the form. So on the last thing, you end up with a 0 form or a function, which is now a length n-3 factorial vector. And this is just to show you that there's an explicit way of doing this. So in each step, you have some vectors here. There's some matrices that have known expressions in terms of omegas from the previous slide. And all you have to do is multiply those matrices together, and they then take some of the residues for each boundary on each sphere. And that builds you recursively the p minus first twisted form. And then the result that you can prove is that intersection numbers on the total space are just scalar products of this coarse-grained phi-3. So you go through this recursion, you land here, and then at the end, all you have to do is just take a product of them, and that gives you a rational function. And in fact, it's the way that we know now how to compute the examples from the previous slides. So all this just boils down to linear algebra, multiplying matrices, etc., and taking one-dimensional residues as was done here. So in the final 2 slides, let me just tell you how this all fits into a bigger picture. So it turns out you can define a whole web of different homologies and cohomologies. And in this talk, we've just been talking about the small corner of the space in which we had these nabla omega and nabla minus omega, and they give rise to intersection numbers. However, you can set up things, for example, such that open strings become just a consequence of a Poincare duality between some twisted homology and cohomology groups. Okay? And similarly, closed strings you can define in a similar way. You just need to introduce some antiholomorphic pieces. And what's the consequence of this? The consequence is that the dualities between such homology and cohomology groups, which induce their pairings, they imply a web of relations between scattering amplitudes and other objects that you can define on the moduli space. So one famous example is that this series of dualities, here, here, and here, gives rise to the relations of Kawai, Lowell, and Tai that relate 2 copies of open string, one copy of closed strings, and the homological version of intersection numbers, which are just some trigonometric functions. Okay, so to summarize, we introduced a new class of objects, which looks like this. It's a wedge of two cohomology classes twisted by some one form, integrated over the moduli space. They are called intersection numbers, and they seem to compute tree-level scattering amplitudes in various quantum field theories directly from the worldsheet. So some of the open questions are, well, first of all, is there a worldsheet action which would generate such scattering amplitudes as intersection numbers? The other question is, what is the space of all amplitudes that admit such a representation? I've just shown you a few examples. And then other natural questions is, can you generalize it to supermoduli or higher genera? Thank you.